Okay, if you've ever taken a science class, you know this feeling. You're in the lab for hours, you're measuring everything super carefully, you follow all the steps, and your final result is just, well, it's off. It's this universal frustration for STEM students. And today, we're going to dig into why that happens and how a really cool, new tech-driven approach is fixing it. Right? You do everything by the book, you crunch all the numbers, but your answer doesn't match what the textbook says it should be. And you immediately start thinking, what did I do wrong? Is this equipment busted? Well, that gap between the clean, perfect world of theory and the messy reality of the lab, that's one of the biggest roadblocks in science education.
And the root of the problem is this kind of fundamental disconnect. In math class, things are predictable. There's one right answer you're looking for. But then you walk into a real lab, and every single measurement you take has this tiny, totally unavoidable bit of uncertainty. The real world isn't exact, it's variable. And that's not a mistake, that's just how science works.
For decades, science has been taught using what researchers call a deterministic approach. Basically, it treats experiments like a cookbook recipe. You follow the steps, you plug your numbers into a rigid formula, and you get the single correct answer. But this method teaches students to see any uncertainty as a failure, when, and this is the key, understanding and managing that uncertainty is what real science is all about.
Now, this whole one right answer mindset, it really causes the most trouble when students run into one particular concept that is notoriously difficult.
It's called error propagation. And think about it like this. If your measurement for mass is just a tiny bit off, and your measurement for volume is also a tiny bit off, when you use those two numbers to calculate density, those small uncertainties don't just add up. No, they combine and they can actually grow, making your final answer even more uncertain. Tracking how that happens is absolutely crucial.
And here's the real kicker. The traditional math for figuring all this out is, well, it's super complex. So complex that it creates what psychologists call a high cognitive load for students. They get so bogged down in just trying to do the calculations correctly that they completely lose sight of the science they were supposed to be learning. To put it simply, the math was getting in the way of the science.
But what if you could just lift that mental burden? A team of researchers in Spain developed a really innovative two-part solution to do exactly that.
First, they created a new educational guide. This guide shifts the whole focus away from hunting for one right answer and toward understanding that experiments are, by nature, probabilistic. And second, they built a piece of custom software called UCA-CPE to do all the heavy lifting of those tricky error calculations.
Now, the engine running this software is an incredibly powerful technique called the Monte Carlo Method. Instead of using those complicated old formulas, the software basically runs the experiment on a computer tens of thousands of times. Each time it uses slightly different random values that are all within the margin of error of your original measurements. What this does is it builds a complete picture of every possible outcome, making the abstract idea of uncertainties something you can actually see and understand intuitively.
So how does this game-changing tool actually work for a student in the lab? Let's take a quick look. So this is the main screen, and right away you can see what they were going for. It's clean, it's straightforward. The whole goal was to create a tool that was super easy to learn, specifically to lower that cognitive load and let students focus on the science, not the software.
In fact, the software was built on 4 key ideas. It had to be easy to learn. It needed to be flexible enough for all kinds of different lab experiments. Of course, it had to be precise, and it needed to be powerful enough to run those complex simulations in just a few seconds.
For your more straightforward tasks, the software has these basic and simple modules. You can think of them like a super-powered calculator. You just pop in a measurement and its uncertainty, and the software automatically tracks how that little bit of error carries through every single step of your calculation.
But this is where the real magic happens. The advanced module actually visualizes the results of that whole Monte Carlo simulation. That graph you're seeing, it shows the distribution of all the thousands of possible outcomes. For the very first time, students can literally see the uncertainty. It's not just an abstract number anymore. It's a shape, a range, a visual concept they can finally wrap their heads around.
Okay, so having a great tool is one thing, but the million-dollar question is, does it actually help students learn better? Well, the researchers designed an experiment to find out. So here was the setup. They took 57 second-year undergrads in a physical chemistry class. They gave them a test on all these error analysis concepts before they did their lab practical, and then they gave them the exact same test after they had used the new guide and the software.
And the test was pretty specific. It measured 3 key areas. First, AMIT. Could they pick the right method for analyzing uncertainty? Second, ACPE. How good were they at actually using the new software? And third, ARS. Could they interpret the results to suggest ways to make the experiment better? Which, is a huge part of being a real scientist.
So, what did they find? Well, the outcome wasn't just positive. It was dramatic.
I mean, the results really do speak for themselves. The blue bars are the students' average scores before they use the new tools. The orange bars are their scores after. It is a night and day difference. Across the board, in every single category, student performance just shot through the roof.
And just to be clear, this wasn't some minor statistical blip. The researchers measured the effect size using a stat called Cohen's d. Now, anything over 0.8 is considered a large effect. As you can see, the effect sizes here are just huge. The total score had an effect size of 3.58, which is classified as very large. This thing made a massive, meaningful difference in their learning.
And get this, it wasn't just that their scores got better, the students felt the difference. When they were surveyed afterwards, they overwhelmingly rated the new guide and the software as highly useful for their learning, giving it scores of 4 out of 5 or higher. So the new approach wasn't just effective, it was also a hit with the students. But the researchers also found something else, a really crucial piece of nuance. They found that even though student performance and confidence soared, their high perception of how useful the tool was didn't always mean they had achieved complete mastery of the concepts. And that's a critical insight from educators, right? Student confidence is great, but you have to back it up with hard data.
Ultimately, what this whole study is about is more than just one piece of software in one chemistry class. It's really about a fundamental shift in how we can teach these really complex scientific ideas. This study proves that by taking the heavy computational burden off of students and by giving them intuitive visual tools, we can unlock a much deeper understanding. It transforms a subject from a frustrating math problem into a fascinating exploration of science. And that leaves us with a really exciting question for the future education. What other hard subjects out there could be unlocked with the right tools?